I'm Oscar Romero, and this talk is on the paper A Long-Term Evaluation of Adaptive Interface Design for Mobile Transit Information. This paper is co-authored with Alexander Haig, Lynn Kirabo, Qian Yang, John Zimmerman, Anthony Tomasic, and Steinfeld. Personalization of user experience has a long history of success. For instance, shopping applications employ recommender systems to reduce the amount of searching the user must do. More recently, the community has focused on adaptive user interfaces, supported by machine learning, that reduce interaction efforts and improve user experience by collapsing transactions and prefiltering results. But if there is a lot of research work in this area, why are adaptable user interfaces so rare? One likely cause might be the lack of evidence that adaptation really improves user experience. Some research shows it can have a negative impact, for example, Microsoft Smart Menus. Another reason may be that the machine learning models that support adaptation perform well in the lab, but the models do not perform well when transferred into the real world. In this study, we explore the long-term implications of an adaptive user interface in a mobile transit application called Tiramisu that reduce the amount of bus route filter selection, scrolling, reading of screens, and other navigation. During the interaction design, we identify patterns of UI adaptation. For instance, our application was redesigned to skip the normal landing page, which lists several options for the user, and automatically select the transit information option. Then, the system automatically computes the most likely bus stops of the user through the use of location information. A random forest machine learning model was constructed to predict desired routes and direction. This model was then executed every time the user visited the transit information page, and the results were used to pre-filter routes and direction. When no adaptation is performed, the output of the transit app is not pre-filtered and the user must scroll down to see all the results. Using the filters on the top, the blue boxes, the user can manually filter out bus routes based on the route direction. However, there is no adaptation. Now, we have an adaptive interface that learns to predict the most frequently routes the user takes given the current context, that is, time and location, filtered by either inbound or outbound direction. Filter buttons are colored differently. Orange shows the filters predicted by the app, while blue buttons show filters selected by the user. We use an A/B study to assess the long-term impact of the adaptation and compare participants in two conditions. In the adaptive condition, the user interface was adapted to participant needs by filtering bus routes and trip direction. In the non-adaptive condition, the system made no attempt to automatically filter bus routes or trip direction. We collected data from 16 participants during an 18-month window. We propose 4 hypotheses drawn from both the literature and empirical data. First, participants in the adaptive condition will select fewer filters and make fewer navigation actions than participants in the non-adaptive condition. Second, participants in the adaptive condition will select fewer filters and make fewer navigation actions, even when the machine learning model generates incorrect route predictions. Third, participants who use the screen reader in the adaptive condition will select fewer filters and make fewer navigation actions than sighted participants in the non-adaptive condition. And finally, participants in the non-adaptive condition will abandon the app at a higher rate than participants in the adaptive condition. Our findings are presented according to the hypotheses that I mentioned earlier. On effort reduction, Hypothesis H1. From the plot on the left, we can observe the users in the adaptive condition perform less filter selection. However, both groups show a trend towards selecting a no filters over time. From the plot on the right, we observe a different trend. The number of navigation actions increase over time for participants in the non-adaptive condition, while decreasing for users in the adaptive condition. Both filter selection and navigation showed statistically significant differences, so hypothesis H1 was confirmed. Now, in order to test hypothesis H1.1, we need to analyze how users in the adaptive condition behave when the machine learning model performs either good or badly. These plots show an unexpected behavior. Those users who perceive a bad performance of the system started making more filter selection and navigation after a certain number of time steps. Therefore, this hypothesis was rejected. One reason for participants in the adaptive condition to continue selecting filters, even when the system performed badly, was that they implicitly may have known that their bus route preferences were somehow learned by the system. So they didn't give up, and in the hope that the system could make a good prediction again in the near future. This effect is known as a trust bias. Now we compare effort reduction on blind and low vision participants in the adaptive condition versus sighted participants in the non-adaptive condition. From the statistical analysis we concluded that sighted participants made significantly more filter selection than blind participants, while blind participants made significantly more navigation effort than sighted participants. So hypothesis H1.2 was confirmed. This plot shows the survival probability estimated using the Weibull test. The plot suggests there is no significantly different abandonment rate between participants in both conditions, since the confidence intervals overlap throughout the timeline. Therefore, hypothesis H2 was rejected. One reason for both groups having a similar abandonment rate may be due to a noise factor, where people left the city or transit, which manifested in the data as an abandonment, for example, a job change, degree completion, etc. In summary, one design recommendation that we take from this study to the community is that the community needs to think better about the dimensionality of the problem when using machine learning to avoid adverse effects of adaptation, such as user frustration and app abandonment. For instance, our machine learning model uses simple features, but modeling travel patterns and human behavior can be much more complex, encompassing changes in lifestyle and routines, occasional changes in trip plans, changes in social circles, and multi-scale sensitivity, and more. In order to build better adaptive user interface, more robust self-reported information and feedback from users is needed, so the machine learning models can be adjusted opportunely to improve their performance, and a deeper understanding of the reasons why users abandon the app can be acquired. We anticipate that the adaptive user interfaces that reduce effort can lower cognitive and interaction load, which is especially important for people with vision impairment and other kinds of disabilities, such as cognitive or dexterity disabilities. We provide empirical evidence that well-performing adaptive interface leads to reduced interaction effort, while poor performance may lead to more interaction effort than no adaptation. The contents of this paper were developed under grants from the National Institute of Disability, Independent Living and Rehabilitation Research. Thank you.